Hi there. So we're now continuing with our revisitation of Gaussian elimination, but we're doing it so that we can identify our first matrix decomposition that arises from that method, so-called LU decomposition. L stands for lower triangular, with a diagonal in this case, and U stands for upper triangular. And once you've got the matrix decomposed in this form, it's a lot easier to invert. Okay, I'll hand over the board now. Okay, so last time we got to this point with a Gaussian elimination of a 4x4 matrix, and what we're doing is redoing familiar Gaussian elimination, but we're making some observations about the matrices we form as a result of that, and that will form part of what's called the LU decomposition. So part of the LU decomposition is the U matrix, which was this triangular matrix here. I'll just do a dash around it. And that's called U, which is upper triangular. So this forms part of the decomposition of A matrix, which equals LU. Remember, the whole point of matrix decompositions is we take a difficult matrix which has elements all over the place, and we decompose it into two simpler matrices which we can solve more easily. And it turns out the U is very useful because it has just a single element in the corner here. So you can easily invert U, whereas you can't easily invert A. And we can finish off our Gaussian elimination solution by reading off our solutions. So if we define a matrix X is x1, x2, x3, x4, and we're solving AX equals B. Sorry, there's no underline there. Let's write that down properly. So matrices here throughout have no underlines. Vectors have underlines, by the way. Okay, X and B are vectors, A is a matrix. That's a notation I'm using, and we'll use consistently throughout this section of the module. So we can these two elements here correspond to x4 equals 4. So it's easy. And then we can evaluate the next line up, which is minus 2 times x3 minus 2 times x4 equals minus 14. And then we just substitute in x4 from the previous line. So that implies that minus 2x3 minus 2 times x4, which is minus 8, equals minus 14, which implies x3 equals 3. And we can call this process backward substitution. To form the solutions. And you can, if you continue with that, you end up with this result. That x4 equals 4, x3 equals 3, x2 equals 2, x1 is 1. So our solution to AX equals B is simply 4, 3, 2, and 1. Sorry, other way around. As easy as 1, 2, 3, and 4 rather. 1, 2, 3, and 4 rather. That way up. Okay. So that's just going through your normal Gaussian elimination. But what are we observing? Well, we had this U matrix, and we had this other matrix, which was our matrix of multipliers. So we want to show you actually that corresponds to how you do some. So in fact, our Gaussian elimination involves a Al U decomposition. So here we take A is Al U. So U was the upper triangular, so triangular shaped matrix with a diagonal elements matrix was the upper triangular matrix at the end of Gaussian elimination. What about Al? Well, it turns out Al is this matrix of multipliers that we basically kept note of as we get through the algorithm. I sort of highlighted. So let's see how that works. So actually, I'm just going to show you this decomposition now for the original matrix. So the original, let's see if I can fit it into this board. Maybe I have to use it 2 lines. So our original matrix was this. That's the one we started off with. So that was our matrix A. But we can now write it as a decomposition, as a multiplication of 2 matrices. So let's just put U in here because we've had that from the last stage. So this is what we ended up with at the end of Gaussian elimination. Upper triangular. So it's triangular, it's upper. The other thing to note with this particular definition of U is that it includes a diagonal. Some definitions include diagonals, some don't, and I'll emphasize that as we go through this part of the module. But in this case, it includes a diagonal. Okay, so that's U. But what about this other matrix Al? And actually, I'm going to equate that to M, which was our matrix of multipliers. So, and so the thing about the Al matrix, it's a lower triangular. So that means it has zeros up here. So this is lower triangular. And this is upper triangular. And these triangular matrices are dead easy to invert because you just evaluate the corner element and then either backward or forward substitute. You go through the matrix upwards and downwards, and that's all fine. So let's remember, if we work back from before, we found that M43, so this element here is M43. Ooh. So that was row 4 plus row 3, and then we took the minus sign, and that goes in there, yeah? And then we just fill in all the other elements. So all the coefficients, like M, so this other element is M12, yeah? M13. So our first elimination of column in Gaussian elimination corresponds to that bit, second corresponds to that bit, and third one corresponds to that bit. Okay, so we've got this lower triangular matrix. So the point is if Gaussian elimination turns out to be quite expensive in terms of calculations and steps, computation expensive algorithm. I'll go along into that a bit more. But if we can, if we've got a single A matrix that we want to do several inversions, so imagine we want to do multiple inversions of A. If we can do this decomposition once, so we just apply Gaussian elimination once, say, then we can then forget about doing Gaussian elimination for further inversions of A and just use our L matrix and U matrix because they're ready-made, if you like, for doing inversions and have this nice structure. So let me just say a little bit more. So L turns out was our matrix of multipliers. So it's M. Sorry, I got the so it wasn't 1 2. It was 2 1. I made a mistake there from previous. So it's 2 1, M 3 1, M 4 1. So just a correction there. That I said 1 2 previously. That's actually 2 1. M3 2, M4 2, and then this element M4 3 1. Then we've got zeros. Fill the zeros in. Okay. So actually, in that, you probably didn't realize it before, but hopefully you do now. Is through all those multiplications of rows, you've been accumulating a matrix called L, which is lower triangular. So if we want to do multiple inversions of A for different values of B, say, instead of doing multiple Gaussian eliminations, which are computationally expensive, we can do one, let's emphasize it even more, we can do a single Gaussian elimination to give A equals LU, then proceed with L and U instead of A. Okay, that's the principle. So let me just expand on this. So if we now have AX equals B, becomes, and we're substituting A as LU, we have LU X equals B. One difficult matrix replaced with two simpler matrices. And let's just rewrite. Of course, you know how matrix multiplication works. You do the ones on the right first, and then the next one. But let's just really make that explicit. That means that we do the U multiplication first, and then an L multiplication equals B. So if we we can then invert L and U in 2 steps. And we do this by saying, let's let this an intermediary vector y equal B, and let y okay. So what I've done is I've split it into 2 inversions. You invert L and then you invert U. Obviously you can check that this is the same as above if you just substitute, if I just substitute the bottom line here, ux equals y, into here, you recover this, L times ux equals B. So we have 2 steps then. We invert L and we invert U. And I hope you agree that inverting L and U, once you have them, is much simpler than just doing it more and more Gaussian elimination. Okay, so that's your first decomposition. And LU is one of the most common matrix decompositions. And there are several others that we don't cover in this module. But it's important in when we talk about matrices, certainly at this level, is that we start to introduce you to this idea of decomposition. We haven't done anything to do with iteration yet, right? That will come. But at the moment we're just doing how can we prepare the problem, how can we manipulate the matrices we're using to make it as efficient as possible computationally. And that the most notable one is LU, and the nice thing is it links with Gaussian elimination that you did last year, and you know, it sort of fits together nicely. So and the point is these are much easier to use, and I hope you see it's actually quite easy. So that's just another example from the notes. Another example is 3 by 3. And this can be decomposed thusly into what happens is, I think sometimes I go to the bottom of my board and it does that. Sorry about that. So we got the OWL matrix. So OWL always has ones. This form of OWL anyway has ones on the diagonal, whereas the U matrix doesn't necessarily have ones. It normally has something other than one. So we're going to do a 3 by 3 example now and just use and assume we've done the LU decomposition, and then use the L and U to invert A in these two stages that I just described. Okay. And you could clarify just by matrix multiplication that this is example here. So stage 1. Solve Ly equals B. Why did I put Y? L equals B. So we invert that. So we're going to choose B, by the way, for this problem. We're going to choose B equals 0, 6 minus 4. So if we take the lower triangular matrix from the previous board or the lecture notes, I would really advise just having your lecture notes out in front of you, like I do actually when I'm teaching this. It's very close. There should be a very close correspondence between these videos and the lecture notes. So if you want it printed out nicely in LaTeX, have those in front of you. And pause the video, any questions you have, and then you can bring those questions to the live session or the tutorials or the practicals. Where you can chat to me. This is Ly, so here we're solving, this is L, lower triangular, Y equals B, and we solve this for Y. And of course, we can do this easily by starting in the top corner. We can actually read it off. We can see that y1 is 0. So we just sweep down, if you like, through the matrix, or we do forward substitution. And by the way, this process of forward substitution is very easy to code. I mean, if you've got a really big matrix, you start off with one value and you just do a loop and you update the values each section. So it's very easy to sort of code it once you've got it in this form. It's not very easy to code Gaussian elimination, really. So that's another advantage. So we have y1 is 0. Then we go to the next line, which is 2y1 plus y2 is 0. And we substitute the value for y1, which is 0, which implies, sorry, not 6, 0, it's 6, which implies y2 is 6. And then the last line, I'll leave you to do that, gives y3 equals minus 6. That's y2 and y3 calculated. And the next step is u times x equals y. So you take the y value from the previous step, so that you write that down as 1, 1, minus 1, 0, minus 3, 3, 0, 0, minus 2, x1, x2, x3, which is our x vector, equals y, which is 0, 6, minus 6. Okay, so you do the same process now. You now sweep up, starting from the bottom corner. So there we have minus 2 times x3 equals minus 6, which implies x3 is 3. And equivalently, you do the next two steps. If you want all the individual steps, are in the lecture notes there. Equivalently, you also get x2 is 1, x1 is 2. So the result here, I'm just going to write it up here, is that x, our x vector, our inversion is 2, 1, 3. And I hope you agree that once we've got these L and U matrices, the inversion process is much more painless, much more computationally efficient than doing multiple Gaussian eliminations. Okay, so I'm going to pause there and we'll come back to that next time.